I'm going to talk about optimization or local optimization for a little bit, and then take a break and talk about, maybe have some comments about project or suggestions about project. Yes, I know the test isn't back yet. Well, patience, patience. Besides which, it's been such a beautiful week. Why would you want to spoil it? Okay, questions? Initial stuff? Good. So last time we had stopped right here. I'm going to have to remind you of a few things. So let's assume, we're going to assume for the sake of this slide that we have converted the program into what was called single assignment form last time. Let's go back and look at that. So again, what that means is that we arrange that every time you set a new value in a variable, you instead create a new temporary variable to hold that, so that at any given time there's a variable that corresponds to each possible value or each value of a certain variable throughout the course of a basic block. Now, this seems kind of strange, and of course it means that you've got all these temporary registers, but the motivation for this will be, as we'll see, that it makes it easier to describe and implement certain optimizations, and at the same time, we're going to rely on later parts of optimization, namely those that deal with how you allocate memory and registers, to undo the damage caused by having lots of these things. So it's a strange sort of way to proceed. We make the program worse, but better from the point of view optimization, but worse overall. Then we do some optimization. Then we make the program. Then we undo the worsening and make the program better than it was before. So, kind of an interesting way to go about it. It's an approach that you might not otherwise think of. Okay, so here's the idea. Common sub-expression elimination, basic classical optimization. It means this: if you calculate something twice, instead just calculate it once. So in this particular basic block, we see that converted basic block. We see that we have a computation of y plus z that occurs twice, and the first time is assigned into a temporary variable. We're going to be doing 3-address code here, and is assigned into a temporary variable. Okay, fine. So the second time we compute y plus z. That's not a particularly interesting operation, I admit, but it is something. The second time we compute y plus z, we'll just use x, because we computed it before and we put it in x, so we'll just use x. That's common sub-expression elimination in a basic block. So, pretty straightforward. Now, the question at the bottom here: why do we have to assume, in order to do this, the way I did it, why did I have to assume single static assignment? Okay, what? Pardon me? That's right. The thing about single static assignment is that a variable, through the course of a basic block, a variable never changes, or changes just once, the very first time it's assigned. And, well, that's not quite true, unless it has a previous value that gets used elsewhere. So we know that x is not changed after this assignment to it because there's a single assignment to x. So it's very easy. Now, of course, we're also using the fact that we're in a single basic block so that we can actually get away with this, but that's another story. Okay, another classical optimization, copy propagation. So, whenever we do an assignment can be treated sort of like an alias, almost. So, for example, where we see in this example, where we have we use 2 times A down there right here. Well, A comes from B, so we could just as easily use 2 times B. Now, and in this case, so why would you want to do that? Well, in this case, the interesting thing is that A might not be necessary later on, so we can get rid, so it could be that we can get rid of this assignment altogether. Here's another example where I have assigned into B, so I use the value of B when I convert this, so I use the value, whoops, typo, make that A. Okay, so let's, from now on, A and B will be the same letter. All right, so I can convert, I set B to 13, or A to 13, and I multiply A by 2, well, that's the same as multiplying 13 by 2. So now, not only could I perhaps get rid of the assignment to B, if it isn't used, or whatever it is I'm calling it, if it isn't used subsequently, but in addition, I can do constant folding, change the 2 times 13 into 26. And there you go. Now again, it says that the block this won't work unless the block is in single assignment form, single static assignment form, and that is because, oh, this was easy. Yes. It's the same reason as before. That's why it's easy, you see. You've got to. So here's a more extended example of this thing going on, in which we start over here on the left, and we propagate down the assignment to A, constant fold it, propagate that down to here, and constant fold it. And we finally end up with something that looks like this, where there are no computation, there's actually no computation at all. It all gets constant folded. So this is kind of this is the sort of thing you can do. Now again, you'll say, well, yes, but why would a programmer ever write stupid programs like that? And the answer is, well, perhaps a programmer wouldn't, but after writing, but after doing some inline expansion or doing some symbolic constants and things like that, your program can turn into, you can easily get programs that have these characteristics. And so, and it's nice to think that your use of abstraction doesn't have to make the program slower. This is actually an important use of optimization in my view, classical optimization. You can feel free to do abstraction without constantly worrying, as we old-time programmers did, that your program is going to slow down by some significant constant factor as a result of all this abstraction. Okay, so we've talked about this next one before, another classical optimization, dead code elimination. So we assign into a variable that is never used anywhere else in the program, and that's dead. So in this particular case, I have done something in which A gets B gets C plus Y. What is this anyway? X mysteriously changes to B somehow. It's very strange. Okay, so let me try to grok this peculiar thing that I've done here. I don't know. I see. I think probably what happened is, oh, I get it. I must have turned it into, this must be my funny way of turning things into single static assignment form. I don't know. It doesn't make a lot of sense to me. I think we have to ignore this. Okay, so we get something on the left. We convert it here and use the fact that A was in fact assigned from B to get this. And then at that point, A is not used, so we can get rid of the statement. I've got to go back and clean these things up. But the idea is simply this: it may be that as a result of doing copy propagation in particular, that you or constant folding for that matter, that you get rid of the need for a statement altogether, and then poof, it's at that point it disappears, and you have saved yourself some computation. All right, so again, the problem with all of these is that any one of them, if you sort of stop after one of them, you have a problem. And furthermore, you can't necessarily apply them. It's not clear how you apply them simultaneously because they sort of chain on each other. So you have a situation where you will often have to do multiple passes until things. You do multiple passes until either things settle down, or you have exhausted the number of you have budgeted a certain number of passes that you're willing to take, and you don't go any further. So, or you have some fixed scheme. We'll do this process 3 times, or something like that. Now, of course, that means that you won't get an optimal. You won't necessarily get an optimal code sequence. There are things called super optimizers, by the way. I haven't mentioned this, but there are these things called super optimizers that basically go in and they look at a tiny piece of their program and they explore all possible code sequences for producing that effect. And they really do optimize. They produce the best code sequence for that particular effect. But of course, you can't do that on a scale of more than a few instructions. And it's highly dependent on not only the architecture, but also the particular release or variety of the architecture. So it's something that you see, and I see it in conference papers. You also see it you saw it in conference papers. It's sort of an old subject these days. And you see it, you see people do things like this when they're really trying to produce a library kernel of some kind that's going to be used very, very extensively in some huge computation that's going to go on for months. And then it becomes very cost effective to try this kind of thing. All right, so here we have some source code. And we'll just apply a bunch of optimizations and see what happens. So we do a little bit of algebraic simplification. Here we have a gets x squared, e gets b times 2. We can change them like that. Now, whether that's necessarily a good idea, I don't know. It depends on the architecture. But this is just this is just an illustration of these things going on. Yes? Left shift 1? Yeah. The fact of the matter is that the answer is no. It's not fast. None of these are actually faster. This is sort of a baby example, because on much modern hardware, because it's just the things just happen. So much happens in a single machine cycle these days that it's hard to. Sometimes these examples get out of date, but. On the other hand, 2 to the or x to the 2, there isn't an instruction for doing that. That would normally be, if you were to do it generally, it would be a procedure call or a function call. And certainly multiplying x by itself is faster than doing a function call that then looks to see how many times it's supposed to multiply x by itself and so forth. All right, now we do a little copy propagation. Here are the red things here show the things that can be copied. And when we do that, we get this, which is okay. And then we do a little bit of constant folding because because as a result of copy propagation, we've got e going to 3 plus 3, so we fold that up. Now we have a little bit more common subexpression elimination. A and D are both computing the same thing, so we can do that. And as a result of all of this, we do some more copy propagation, on A and E, and that gives us this. Now we have a whole bunch of variables that we don't use, assuming that A and so forth are all things that are, or B and so forth, they're all temporary variables that have been introduced as compiler temporaries. We get this, and this is this code is considerably faster than what was before. It's kind of interesting, I think. Pretty simple example. Now you don't. This looks kind of dramatic. It is kind of dramatic. Just out of curiosity, can anyone guess, sort of ahead of time, what do you suppose is a very rich source? Can you name a very rich source of sequences of optimizations like this? Where would you expect a bunch of, where a naive code generator, even with an ordinary program that isn't especially intended to illustrate common subexpression elimination or anything else, how an ordinary program might come up with a huge sequence of optimizations like this that lead to a dramatic shortening of the program? Can you think of an area where this might happen? Yeah. What do you?
If we're using the intermediate language and we're making it in registers?
Yes, that's certainly a general area. I'm thinking of a particular program construct where this kind of thing is likely to arise. Yeah.
Code that's never called.
Yeah, but let's assume for a moment. Okay, that's true. But assume for the moment that I'm the kind of programmer that I've trimmed this sort of stuff out of my program. I don't leave all that crud around. So it's my program is already trim as far as so it has only the code that I use. But there's one area that really generates a lot of this stuff. Yeah.
For loop?
Yes, a for loop. Well, yes, for loops, and in particular for loops with arrays. That is, list things. Because if you remember from a few lectures back, the code, the 3-address code and stuff for accessing arrays generates lots and lots of stuff. And you really want to, and that can really be, and getting rid of that, making it nice and tight, is a good source of optimization. It was a historically good source of optimization. Now, we have another flavor of optimization altogether. It's called peephole optimization. So in this, what you do is this goes down to assembly language or to something, a low level of the program. And what it does is it's tailored, it refers to optimizations that are tailored to a particular architecture and that look for opportunities where some sequence of instructions, either immediately adjacent to each other or linked by register dependencies. In other words, this instruction uses a register, it sets a register, this instruction uses it, there's nothing intervening that sets that register. It looks at a peephole, a few instructions at a time, and from its knowledge of the architecture, it makes something better. There are some that are generic. For example, let's see, what we've got here. So here's an example where we see a move of A to B followed by a move of B to A. So we can simply replace this with a move from A to B and ignore the second instruction. We could also have done that at a higher level, but you can. This particular optimization you can carry out at the peephole level. This one is here's one in which I add something to a register or to some variable, and then I do an indexed offset, something indexed off that register into B, Well, I can simply add the constant that I was going to add ahead of time, like this, and get this into one instruction, assuming that I don't need this. And here's one of my favorites. This is converting an instruction into a shorter form of the same instruction on the PDP-11. So suppose that you want to put a certain immediate value into a memory location. So I want to move this immediate value here into a memory location, into this memory location, and it just happens that the value of the thing the immediate value that I'm storing, the constant that I'm storing, happens to be the same as the index, as the displacement into the memory. This is a real optimization, by the way. It was done by a certain compiler of from my distant past. No, not my distant past, but that from my graduate student days. There was we had a compiler at Carnegie Mellon that was doing this sort of thing. So what this thing does is, on the PDP-11 had a very interesting and elegant instruction set, in which essentially every operand was its own little mini instruction. And it told you, each operand told you, load from this register, or load from this register in increment, or something like that. And so the way it actually worked was that this instruction here, move indirect off R7, which was R7 was the instruction pointer. So at the time that you did the indirect reference from the instruction pointer would be pointing into the middle of this instruction, right at the place in the instruction that holds the displacement value for the next operand. And so it would move part of itself into the destination. Yes, this is a colossal kludge. You do not want to do this at home. You want to leave it up to the compiler. But it shortened the instruction by 4 bytes or something like that. So it's this is peephole optimization. There is no way you can represent this at the high level. I mean, this is just it doesn't make any sense at the high level, but at a peephole level it does. So I should say something about peephole optimization. It's kind of interesting. In the old days, they moved away from this, but GCC used to have this structure in its optimizing compiler where basically what it did. I'm sorry, they still have it to some extent, and they're trying to transition away from it, and I don't quite know where that stands at the moment because I haven't looked at GCC for quite some time. But their strategy was generate a bunch of code naively, do common subexpression elimination and a few other of these simple things on that naive code, and then do peephole optimization that converts the code into good stuff. And that was called the Davidson-Fraser code generator, and it did an okay job, but it was sort of limited in the sorts of optimizations you could do, and they've since moved to a more elaborate, to actually an unholy conglomeration of a more elaborate scheme and this old scheme. So it's I don't quite know where things stand at the moment, but this has actually been used to do real optimizations. So what's so great? So all right, so I've described some optimizations. It sounds good. Oh yes, optimization, good for the program. It sounds nice. Unfortunately, we run quickly into certain problems. So pointers, or anything that's any reference to memory, is a real problem, because every time you store through a pointer, so I say star t equals something in C, every time I do that, some memory location changes depending on the current value of t. And it might or might not have an effect on star r, no matter how unrelated star r is to star t. So as a result of this, now these pointers can come up even in languages that don't have pointers. For example, in Fortran, didn't have pointers. You can still have array parameters, and these array parameters are represented as pointers. So the compiler sees them as pointers. And so there's a rule in Fortran that says that you may not have, that these parameters are assumed not to overlap. Arrays are assumed not to overlap. So in other words, the pointer values may be assumed to be distinct from each other, or the memory locations pointed to by the pointers into these two things may be assumed to be distinct from each other. And C has a keyword, a restrict keyword, that has essentially a similar meaning. And that's an example of language design being affected by concerns for optimization. Unfortunately, this helps only to a certain extent within a single array. I have a sub I have a sub j. I and j are two different variables. That doesn't mean that a sub I and a sub j are two different variables, because I and j could be the same. So as a result of this, when you get into the researchy side of things, you'll find that there's work on how do you determine whether pointers, what analysis, static analysis can you do to determine whether two pointer variables contain pointers to the same or overlapping objects. And actually there are I haven't mentioned other language rules that also affect this. For example, in C, if you have two pointers of two different types that are pointing at the same thing, then basically what the reference manual says is all bets are off. This could not have happened legitimately. Well, okay, there are some exceptions to that, but generally this can't have happened legitimately. Therefore, I'm just going to pretend. Therefore, you compiler, you are free to pretend that these two things are distinct from each other. And if the programmer made a mistake and they aren't distinct, well, you will punish him by generating code that causes obscure errors, and it will still be correct because the language spec said that the result of executing that program is undefined. So anything you do is okay. So make the code fast and let the programmer suffer if he's done something stupid. Yes. So you will see an obscure error message occasionally from GCC at high optimization levels that says something like something about type aliasing, blah, 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 and this is a warning that it's detected that you may have done something stupid. It can't detect all of them, but it detects that you may have done something stupid. All right, what about global variables, calls? Here's another problem. Global variable. I say x gets 3, where x is defined outside at the global level. And then I call a function. Has x been changed? If x is a local variable, then the answer is no, unless I've called a nested function. But unless I've called a nested function, or what in C++? What else could I have done? I have a local variable, local to me. I call a function that's not in me, that cannot see that variable. Could the variable have changed when I come back from the function? Hint, not in Java. Right? Pardon me? How can it change? That's right. So if I take a pointer, so you'll find the compiler will suddenly get conservative if you ever take a pointer to a variable. It'll say, okay, anytime you call something else, that variable might have changed. Anytime you assign to a pointer, that variable might have changed. So at this point, you have made your bed, now sleep in it. Okay. So so first of all, these calls are kind of special. For one thing, you can treat them as taking you out of a basic block. Sometimes it's convenient not to, because they almost are guaranteed to come back to the next instruction. And sometimes if you know something about the function, if you know that it's an intrinsic function or something like that, you know it's well behaved in certain ways. So you can sort of get it to work as basic blocks. But you might have to be conservative and just say, okay, this call is the end of a basic block, and the next instruction is part of another basic block or something like that. But in any case, this is going to be a problem. First, because you don't know what global variables might get modified, and you don't know what pointers might get saved. It generates lots of different problems. So these are issues that make optimizing compilers interesting, especially when we turn to parallel computation. All right. So that's a brief overview of, and about as deep as we can really get into in this course, into what happens at the basic block level with optimization. And the next question, of course, is what happens if we put those basic blocks together into a program. But before we get into that, I'm going to spend a few minutes talking about the project and a few responses to bug submits and the like. But first, let us take if there are are there further questions about this? Then we'll take a break. Let's take a brief break, a couple minutes. With what?
Loop harmony. You mentioned that a lot of the areas for these optimizations should be done.
Well, consider a just a simple example. I have something like, let's see if I can come up with something. So I have a loop in which I do, let's see, out of chalk. So just at the most basic level, if I convert for I equals 0, I less than n, I plus equals 1 body, if I convert that into for I equals 0, I less than n, actually I less than n minus 2, I plus equal 3, so enrolling 3 times. And then I have b, I plus equal 1, b, I plus equal 1, b, right? I plus equal 1. And then at the end, I have to have something to take care of the last 2. All right. Well, this, and this will all be subject to algebraic manipulation. So all of the places in B where you see an I, you will be able to replace it with, here you'll be able to place it with I plus 1, and here you'll be able to place it with I plus 2. So the I and the offsets, you won't have to do any of these. These can all be eliminated. The tests on I are all eliminated just by the unrolling. If you've got a variable, if you're doing a reduction, so that you've got this variable that's being accumulated each time, well then you can see that since you will see that in fact where exactly you got the previous value, and you may be able to have a single instruction in which you do all of them and keep it in there. So there are lots of little things like that where it'll help.
So It's usually going to happen even more so in an online context.
Yes, anytime you've got, the more code that you get, because this is a basic block. When your basic blocks get bigger, you can do more local optimization. So,
Like what the customer will do is like you meant this, like my instruction language calls you. This is what you're asking about, right?
oh yes, okay.
Oh, okay. Yeah, I didn't really get what you're saying. That's just kind of part of my job, at least in the way we're splitting up the work.
I see. Well, for each child. Well, this is, so this is what your caller is doing. I'm more interested in, there's this, actually, this was one of the things I was going to talk about, so let's talk about it. In lecture, yes. All right. All right. All right, let's get started. So I'd like to, from time to time, as I encounter them, talk about various issues that you might be facing. First of all, let me iterate something that I said from the previous project. There are certain things I do not want to see, and they are easy for you to fix. And first, I really would like people to develop a sort of sense of aesthetics. What does clean? What does it mean to have code that's actually formatted so as to be readable? And some of the skeleton code is sort of closer, obviously closer to what I have in mind than what I've been seeing. I mean, I don't know. I'm not exactly sure what it is that what causes people to write very, very long lines. Can anyone give me any insight to this? For example, do you set your editors so that you're using these pernicious big screen editors that sort of where you have to go like this to see from one end to the other, and you're just having your line march all across like that? Don't do that. I mean, keep things neat. Okay, so that's a generic thing. And the other generic thing, of course, is when you find that when you're doing tree traversals in particular, and you find that you're querying the type by whatever means, you're querying the type of your children or of your parents, stop, think. This query here is a virtual function trying to get out, right? That means that I'm doing. So if the subtype of, or if the type node, the tag node on child 1 is identifier, then do this. If it is indexing, attribute ref, then do that. If it's subscription, then do that. That just tells you what you're doing to that node is generically the same thing. You're generating an assignment to it, or you're doing something else like this. So there should be a virtual method, generate assignment to, or assign to, or something like that encapsulates that particular action. The sign that you're doing things right is that your methods will generally be relatively short, numerous and short, and each one of them will be understandable. Each one of them, you'll be able to get your mind around it really quickly by looking at it, because you'll know what the method, there will be a description that applies, there will be an overall description that you put on the initial declaration of that method up at the top of the hierarchy. It will apply to all of them, and you'll be able to say, oh, well, yeah, if I want to assign into a subscripted node, then yeah, I've got to generate this code or generate this code or do this analysis, and yep, there it is, and it'll be obvious to you. I mean, trust me, this really will help to clean up your program. But of course, it is necessary that comment at the top be sufficiently descriptive of encapsulate just exactly what this thing is supposed to do. It should have a well-defined task, and that's described in that comment that you can go back to and understand. Just always think of this as if a reader were looking at this comment, if somebody who'd never seen this code were looking at this comment, would it help him understand the program? Would he be able to avoid thereafter, would he be able to avoid looking at the bodies when he calls it? You know, that's the thing that you're shooting for. Okay, but those are comments that I've made in previous projects. Now for this project, a couple of things have occurred to me. One of them is, now a number of you have, I'd like to present them as, well, no, the first one, talking about interfaces. Now, one of the things we've invited you to do, and you don't have to, but we invited you, is to think of putting in an intermediate code layer into your program. Well, what would that look like? You have a couple of choices. One choice, of course, is to actually have a separate data structure, which is intermediate instruction. And you accumulate a bunch of intermediate instructions, and then you go through and you separately go through in a pass and you generate code for them. Okay, that's fine. That might not be necessary. You can probably do something where you generate these instructions and the calls that generate them also, at that point, generate IA32 machine language. Either technique might work. Either technique could work depending on what you'd like to do, what else you would like to do with the intermediate code. The second technique is particularly easy with a stack machine intermediate language. But here's the first question. The first question is, okay, if I make the decision that I'm going to go to an intermediate language of some flavor, the first question you have to ask is, okay, what are my partners who are going to be calling this thing? What are they going to be? What calls are they going to be making? What, in other words, is going to be the interface to this intermediate language? So you could make a parallel. For example, you could choose to make it parallel to what I have in IA32 utils. You have a bunch of emit calls. They take virtual machine operations, virtual machine instructions, and they do their thing. But you really have to nail this down. You want to define this at the outset. What is the procedural interface or whatever method interface to my virtual code generator, or not to the generator, but to my virtual code emitter? Right? What is that? What are people going to call? And I suggest that you write that before you figure out how you're actually going to represent intermediate code. Here's the test. If we imagine that your partners are writing these code gen routines for each different kind of node to generate code, and they're calling your intermediate language interface. If it makes a difference to them, if it makes a difference in what they have to write, whether you choose to immediately generate IA32 output in the calls to your intermediate code, or whether you save them up as a separate data structure and then run over them later, if that makes a difference, then you're doing something wrong. In other words, if I say if your interface should look something like, here's one way of doing it. You say something like emit, and then you have, let's say, a virtual memory, an intermediate language push. So you're doing a stack machine, intermediate language push, and you have some operand. So that's what your partners are going to be writing. If they have to change that when you decide halfway through, oh gee, I really have to save up these intermediate language instructions after all and generate code afterwards. If they have to change it as a result of that decision, then you've done something wrong. Because there is no reason why this call can't work for either representation. And this is sort of a basic principle. It's called separation of concerns. You are concerned with how you get from intermediate language to IA32. They shouldn't be. And the whole idea is, and you shouldn't be concerned about how they figure out, you should not be concerned about how they figure out which ones of these things to call. In other words, if you're designing this intermediate language thing, and you suddenly, and you have a question along the lines of, well, will your code gen procedure be doing this, be calling this, or will this other thing be calling this, then you're doing something wrong, right? You shouldn't even have to think about that. You shouldn't even know that this is a Python, well, that's not quite right. You could, if to the extent possible, it would be nice if you didn't know this was a Python program. This is intermediate language, and you're just doing what you're told, and you don't care how they figured out how to do that. So there should be a separation, and what you do is you figure out ahead of time what it's going to be, what the interface between you and your partners are going to be. You write that down before you even start thinking about representation. Yes, of course, there will be feedback sometimes. You'll say, oh, gee, I really can't do it this way because I won't have enough information. So in that case, you'll have to have a negotiation with your partners about how changing the interface. Don't change it without negotiating it, but keep that in mind. Okay, so that's just sort of one question that has come up about how do we design these things. Now here's a puzzle for you. We discovered. Oh, gee, I won't be able to get into global optimization. Oh, well, too bad. We discovered that the Mac doesn't have a bunch of features. Okay. Pity about that. But I claim that, in fact, if you really want to do code on the Mac, you can. I believe you can do it without changing the IA32 utils interface. In other words, you can make it so that, for example, the instruction emit text subsection, where it says you can redirect text instructions into one of several different chunks and then put them all together. Very useful for separating out the executable code of the module from the defs. You can do the defs in one section, and you can do all of the main program in the other, and it works out very nicely. Oh dear, the Mac doesn't allow that particular assembly language instruction .text1 or .text2. But I claim that shouldn't matter to you. That in fact, you could re-implement IA32's utils in a pretty simple, and it's actually a pretty simple re-implementation to get around that fact invisibly to the programmers who are using it. How do you suggest we do that? Now, I've told you that it's possible. At this point, once you realize it's possible, it should occur to you how to do it. It should have occurred several seconds ago. Come on. How would you do it? Yeah. Yeah. Okay. Yeah. That's one technique. You can stick jumps at the end every time you switch sections. Yeah. That's one way. I'll bet you could do it without that. However. Yes. Change what? To change the specific. Yeah, but you don't need. I mean, the code is always going to be the same. It's just where it's going to be put. Is it going to be assembled into section 1, or is it going to be assembled into section 2? So if you've looked at the emit text instruction, specifically there's this discussion. You can use it to send text to. You can put instructions in one part in one. Segment, or in another, not segment, but one area or another area. And all the things that you put into area 0 will be contiguous, and all the things that you put into area 1 will be contiguous. But you can interleave the generation of them, and it will keep track of it. Yeah?
Can you write it in 2 files and concatenate them at the end?
Yes, you can write it into 2. Well, you don't have to use files. You can use, in C++, there are these string streams. So you could simply have emit text. When it sees that argument, it can say, okay, from now on, I will set the variable, I will, instead of putting everything directly into cout, I will have a bunch of strings that I form. It just so happens that in C++, all of the instructions for writing into string streams, that is, which are streams that are kept in memory rather than put out to a file, all those instructions are identical. Most of the code in IA32's utils would not change. The only thing that would change would be instead of sending things to cout, you send them to the current stream, whatever that is, and the emit text procedure just switches the stream from one to the other. And you don't even have to think about, at the end of the program I have to write these two. You don't have to, the client of the module doesn't have to think about that, because there just happens to be this routine that currently does nothing, called emit trailer, that says do everything that's supposed to happen at the end of the file. Well, nothing says you can't actually do something in that function. At the moment it's empty. So this is just an example of a way of thinking of how abstraction can save you. You don't have to, just because you make some major change in the way you represent things, does not require that everybody else that's using it also change their code. And so I invite you to look for other opportunities to do things like this. All right, fine. I've kept you over, so have a nice weekend.